A rectangular wing can fly. Yes, but it's quite inefficient and not very safe. At zero angle of attack, it can't produce lift because the pressure on the upper and lower surfaces is the same. To make it take off and stay in the air, it needs a larger angle of attack. But why? When it comes to lift, there are basically two formulas to understand it. One that's a bit more complex, and another that's much more familiar. The more complex one is the Bernoulli equation, which comes from the Navier-Stokes equations. By simplifying it for an ideal fluid, that is, neglecting air viscosity, we get the Euler equation. Then, assuming steady flow, incompressibility, and integrating along a streamline, we obtain the more familiar form known as the Bernoulli equation. According to Bernoulli's principle, flow velocity is inversely proportional to static pressure. The faster the flow, the lower the pressure. Over the wing's upper surface, where the curvature is greater, the streamlines contract, the velocity increases, and the static pressure drops. Along the lower surface, the flow is smoother, the velocity lower, and the pressure higher. Another well-known principle is Newton's second law, which states that the net force equals the rate of change of momentum. When the angle of attack increases appropriately, the airflow along the lower surface of the wing is deflected downward, changing the direction of its velocity vector, and thus its momentum. According to Newton's second law, this change in momentum indicates that the wing exerts a force on the air. According to Newton's third law, the air exerts an equal and opposite reaction on the wing, whose vertical component constitutes an important part of the lift. Finally, a more academic concept is circulation. The airflow around a wing forms a loop, and the strength of this loop is called the circulation. Bernoulli's principle explains the pressure difference, but it cannot tell us where this pressure distribution comes from. Newton's law explains the force, but it does not provide a quantitative measure. Circulation, on the other hand, explains the origin of lift and provides an analytical and quantitative relationship. Mathematically, the circulation gamma is defined as the line integral of velocity along a closed contour C. If the airflow velocities above and below the wing are equal, the integral is 0. If the velocity above is greater and the velocity below is smaller, the integral becomes positive, indicating a net circulation, that is, a non-zero circulation, which represents the typical flow condition around a wing section. In a three-dimensional flow, countless streamlines can be regarded as forming a flow surface within the velocity field. Integrating the rotational strength, vorticity, over this surface corresponds to the circulation in the three-dimensional case. From this, the Kuta-Joukowski theorem further provides the quantitative relationship between circulation and lift. The lift per unit span of a wing is proportional to the free stream velocity, the fluid density, and the circulation. Therefore, a wing generates lift because it induces a non-zero circulation in the surrounding flow field. The greater the circulation, the stronger the rotation of the flow around the wing, leading to a larger velocity difference and pressure difference between the upper and lower surfaces, and thus a greater lift force. In other words, Bernoulli and Newton tell us what the phenomenon of lift is, while circulation explains why this phenomenon occurs. Thank you for your patience and for watching. If you're interested in more aerodynamic analyses and simulations, please stay tuned to L'Avion Idéal.